Hey everyone, my name is Nikhil Chari and today I'll be presenting my Raspberry Pi security camera project for CNIT 176. This project combines a Raspberry Pi, a USB webcam, Motion Eye, and Dropbox cloud integration to build a working solution that detects motion, captures footage, and stores it off the device, all with automation and control through Linux. Let's look at the overview of the project. The idea was simple: turn a Raspberry Pi into a functional cloud-connected security camera. This project came out of my personal interest in cybersecurity and real-world system design. I wanted to learn how to manage devices at the system level, interact with files and systems and hardware, and build something practical, not just theoretical. The goal was to build a system that could detect motion using a camera, capture video or photos, and automatically upload those files to a secure cloud location, in this case, Dropbox. Next, let's take a look at some connections to architecture. First, input and output. The core input of the system is the USB webcam. When connected, Linux exposes it through /video0, which is a device file interface. I used a utility to verify that the camera was detected and working properly. Once confirmed, I added it as a device inside the MotionEye interface. The output happens in two forms: live video feed via the browser-based interface, and captured image or video files whenever motion is detected. Real-time responsiveness is a critical part of the input-output. MotionEye pulls the camera continuously and reacts to frame differences, which is what enables motion detection. Next, let's look at file systems. File system management was essential to this project. MotionEye requires a few key directories to function: /MotionEye and /var/libraries/MotionEye, which stores the captured media. These folders didn't exist by default, so I created them manually and set their permissions using chmod and chown to ensure that my user could write to them. I also created a custom folder, MotionEye Uploads, where files are stored temporarily before being synced to Dropbox. I use timestamp subfolders for organizational clarity, which mimics real-world practices in surveillance logging. This taught me a lot about how Linux handles ownership, access control, and directory structure for persistent services. Next, configuration. This is where the system really came to life. I installed MotionEye manually in a Python virtual environment, which helped isolate its dependencies from the global system Python. I modified motioneye.conf to set paths, enable the web UI, and configure motion detection behavior. I then wrote a startup script that activates the virtual environment, recreates required runtime folders like /run/motioneye and /var/log/motioneye, and sets file permissions. I also made sure it launched the motioneye server cleanly. For cloud integration, I installed rclone, configured it with Dropbox using OAuth, and created a bash script to handle file uploads after each motion event. This setup was lightweight, transparent, and modular. Next, networking. Networking played a key role in enabling control and cloud access. I configured the Raspberry Pi with a static IP address so that the MotionEye web interface was always accessible at a fixed location. I used hostname -i, ping, and ifconfig to verify connectivity. I also was able to edit config files and restart services from my Pi. For uploads, rclone used HTTPS to connect securely to Dropbox's API. OAuth authentication ensured that the system had a secure, revocable token for file transfer. This project gave me a practical understanding of multiple networking layers, from TCP/ICP for transport to HTTP for API requests. Let's take a look at system components. Here's a summary of the core components I used: Raspberry Pi's OS, which is the base operating system that runs everything; MotionEye, which handled the camera, motion detection, and live feed; rclone, which I used to sync files to Dropbox through encrypted connections; shell scripts, which automated startup, folder creation, file permission, and cloud upload logic. Together, they made an extensible system that worked properly. Next, let's look at the procedure and a detailed breakdown of how I built the system. I first started off by installing MotionEye in a Python virtual environment so I could avoid package conflicts. I connected the USB webcam and verified it. I then configured the camera in MotionEye and tested real-time feed. I then tuned the motion detection thresholds and minimum motion frame count. Next, I installed and configured rclone with Dropbox using rclone config. I then created a folder for local storage of captured media. I wrote a bash script that uploads media to Dropbox via rclone copy. I configured MotionEye to trigger the script after each motion event using run a command, which is part of the MotionEye menu. I then built a startup script to automate all folder creation, environment activation, and service startup. I finally ran multiple end-to-end tests to ensure files were consistently uploaded after every motion detection event. Now, let's look at the results and a short demo. The final system works exactly as I intended. When motion is detected, such as someone walking past the camera, MotionEye immediately captures a short video and a snapshot and saves it to the local upload folder. Then, the system automatically runs my upload script, which pushes that file to Dropbox. Within seconds, the footage appears in the cloud, timestamped and sorted into folders. The live feed is available through any browser on the local network. In the live demo, I'll show the motion being detected, the file being created locally, and the upload appearing on Dropbox shortly after. Here's a short demo.
We start off by navigating into MotionEye and starting up the virtual environment. Next, I use a command in order to start up the actual MotionEye software. As you can see, it gives me a message that it started up. You can now see that I am showing up on the camera. Next, all I have to do is trigger some motion by waving. As you can see, the red means that there's motion activated. And now when I look at my Dropbox, you can see that there's files appearing.
This project involved some serious troubleshooting, especially since I installed everything manually. First, MotionEye wouldn't start. The error was that multiple files did not exist. I fixed this by modifying my startup script to recreate that folder and the files and set ownership to my user. That way, everything was going to be ready and able to be created by the time the system starts. Second, file permission errors broke uploads and logging. MotionEye couldn't write files, and rclone failed because of this. I learned to check file ownerships and fix them, giving myself access to everything. Third, this one took a while to catch. The run a command feature in MotionEye didn't actually run my upload script. I eventually realized that MotionEye runs it with a minimal environment. It didn't know where rclone was installed. I fixed this by hard-coding the full path to rclone, making sure the script was executable, and logging output to a custom file so that I could see what happened when the script ran. Finally, I fine-tuned the actual motion detection. At first, it didn't register small movements like hand waves. I had to adjust the threshold and number of motion frames until it captured reliably without too many false positives. These fixes helped me understand real system integration, how services run under constrained environments, how to debug file paths and permissions, and how logs can guide you to the root cause of a silent failure. Now, some final thoughts. This project taught me that manual installs don't do any hand-holding, and that's a good thing if you really want to learn. I learned that virtual environments are a clean way to isolate dependencies, but they come with their own challenges. Forgetting to activate them or misplacing a path can break the service entirely. Because of this, I had to make sure that I always created the files and made sure that my automation created those files for me. I also gained a much stronger understanding of Linux permissions. Most of my early bugs came down to incorrect file ownership or missing write access. By working through these problems, I learned how to troubleshoot services, follow logs, and use shell commands more effectively. Every time I fixed an issue, I didn't just fix a symptom, I learned something about how Linux works under the hood. Next, let's look at some future ideas to expand this project into something even better. First, I could try switching from Dropbox to a self-hosted cloud. This would give me a lot more control over privacy, reduce reliance on third parties, and allow deeper integration with custom systems. It would also make the system fully local if I needed to, ideal for secure environments where I could be disconnected. Next, I'd like to add multi-camera support. Since MotionEye supports multiple feeds, I could set up multiple Pi cameras around a space, each monitoring different zones. A central server could aggregate all the feeds for unified viewing, alerts, and storage. Another thing I could add is event-based notifications. I could send email or push alerts when motion is detected and a file is uploaded. This would make the system more interactive and useful in real-time security scenarios. And finally, I could integrate smarter detection with a different AI. I could filter motion events by type, humans, pets, or objects. This would greatly reduce false positives and move the system closer to commercial standards. These additions would elevate this from a simple project to a real-world surveillance platform. Thank you for watching my presentation. I really enjoyed building this project, both for what it taught me technically and for how it challenged me to solve problems hands-on.